Hi, my name is Gregor Skylager. Today I'm going to present harmonics and harmonic mitigation. Before we start looking into what harmonics are, we need to understand how a frequency converter is built up. And how a frequency converter is built up, or the normal input circuitry of a frequency converter, you can see in the upper left corner of your picture here on your screen. And you can see that there are some basic components you need to understand. There are the diodes. In this case, they are numbered from 1 to 6. And then there is a capacitor. In this case, it's marked with VDC, the voltage across the capacitor. And starting with the diode, what is a diode? A diode is a component that is only allowed current to go in one direction. And you can have the analogy to the water world, where you have a one-directional valve. It's only allowing current or water to flow in one direction. If you try to have it going in the opposite direction, you will see that the water is blocked off. It's the same thing here in the frequency converter. The current can only go into the frequency converter. It cannot go back to the grid. Then the second component you have to understand or learn here is the capacitor. And the capacitor is a component that we use to keep the voltage high or constant. And the reason why we want the constant voltage on the DC is simply then we have the better control on the motor. Again here, the analogy to the world of water, if you have a container-like component here, it would be a container where you can fill in water from the top and you can drain it from the bottom part of the container. And here you can continuously drip in water from the top and you still have a constant flow from the lower part of the container. The same in the frequency converter. You can put in current, you can put in energy to the top of the capacitor, and then you can constantly drain energy from the capacitor. Now, if we look at the input circuitry here, we want current to go from the grid side into the frequency converter through the diodes into the capacitor. And if you had the same in the world of water, you need water to go from this container into that container, and there needs to be a condition in place for this to happen. And the condition is that the water at this level, of course, has to be at a higher level for water to go into the cup. If I try to put it from the lower level, then the water won't flow. It's the same in the frequency converter. If we want current to go from the grid into the DC link, then we need the voltage on the input side to be higher than the voltage on the DC side. And you can see the voltages on the grid side compared to the DC link in the middle left corner here, where you have the gray, which is the DC link voltage, and you have the blue, which is phase A, and the red is phase B on the input side. And when you compare the two conditions, you can see that there is a very short window of time where you have the conditions where current can go from the grid into the frequency converter. And that little narrow window is marked here with two pulses. It's light blue pulses you see, and that's actually where the current goes into the frequency converter. I only showed here a fractional of the full current window. So actually what you will see in the current is that you have two positive followed by two negative current pulses, and that's normally what you see when you're putting in a scope in front of your frequency converter. You can see exactly this current window or this current draw. Now this phenomena is not just for frequency converter, it's actually the same current picture you will see when you have a switch mode power supply. If you have a UPS or fluorescent light installation, you will see exactly the same current draw. Now this hasn't told you anything about harmonics yet, but to get into that you need to start doing some math. And there was this French mathematics that found out that you can represent any continuous waveform by sinusoidal waveform. So if you have a square-shaped waveform, you could actually decompose that to sinusoidal waveform, and then you can represent the squared wave waveform. And in our case, it wasn't a square wave, it was a two positive followed by two negative pulses that we had. And again here we can do the same with this Fourier analysis and FFT, fast Fourier transformation, where we are transforming the pulse-shaded current waveforms into a sum of sinusoidal waveform. And I'll guide you through that setup. So the first you will see is that we have what we call the fundamental frequency, the 50 Hertz, and it's a 50 Hertz current waveform. In this case, the RMS value is around 40 amps. And if you're representing that with a frequency spectrum analysis, you will see that it represents 100% in magnitude. Now what we want to generate is these two positive followed by two negative, so we need to add more sinusoidal waveforms on top of it. And the first one we add is the fifth harmonic. And the fifth harmonic in this case is 5 times the fundamental frequency. So if the fundamental was 50 Hertz, then 5 times the fundamental in this case is 5 times 50, 250 Hertz. So the frequency is faster than the first verse. And you can also see that the amplitude of the frequency is smaller than the first is. So in this case, the fifth harmonic, you can read it down in the lower level. It's around 70% of the 100 or the first harmonic. And that also means that we are no longer having the ideal current waveform. We're having a distorted waveform. And normally, when we're talking about distortions in the world of harmonics, we're talking about total harmonic current distortion or total harmonic voltage distortion. And we shorten that to THID or THDI, THDV values. And in this case, you can see it on the picture. The THID value is 78%. And that simply means that we are 78% away from the ideal sinusoidal waveform. Now, we wanna make a 2 positive followed by 2 negative pulses, so we have to add more sinusoidal waveforms on top of it. And now we have added the 7th harmonic. In this case, it's around 50% of the fundamental in magnitude. You can see the RMS has gone up now where we have added 3 current waveforms together. The RMS value is at 54% now, or 54 amps, sorry. And the total harmonic distortion is 100%. So we are 100% away from the ideal sinusoidal waveform, you can say. Now we add another one. This case, it's the 11th harmonic, 11 times 50 Hertz. That means 550 Hertz. That's the frequency of the 11th harmonic. And the magnitude in this case is around 30%. So now, when you look at the sum of 4 sinusoidal waveforms and you sum these together, then you have this representations of 2 positive followed by 2 negative pulses. Of course, you can add more and more to it to make it more ideal and more representing the current waveform we saw to begin with. But I think I'll stop it here. It's simply giving you an idea that how you decompose a signal into sinusoidal waveform. That is actually what harmonics is all about. It's a way of representing a current with sinusoidal waveforms. And what this tells you is the first harmonic is actually the one we use to generate torque to the motor. It's 40 amps. But what we are blocking on the grid is the 55 amp. So cables, transformers, power supply somewhere has to be able to deliver 55 amps. But the motor we are driving, the torque we are generating on the motor is only done with 40 amps. So we are blocking the power utility more than what is needed. We are overloading or oversizing. We have to oversize the cables compared to the current we're needing for generating torque. That alone is actually not a problem. It's just a matter of sizing. And actually what we have done in our frequency converters from Danfoss is that we have put in coils simply to avoid this. So when you're buying a drive from Danfoss, there is always a choke inside the frequency converter, inside the box. And that means that you are not seeing this dramatic oversizing on the current. We are down to maximum 40% current distortion. And that means that basically you will not see the effect of having to oversize current anymore. There are, however, another issue you need to be aware of, and that's the voltage distortion. And That is actually the important part. The current you can park, because we have already addressed that, at least in Danfoss frequency converters. There might still be other frequency converters out there where you haven't built in the choke, and there you need some extra equipment to get to the same performance level. But the impact on the voltage is the important part. There was this guy finding out that there is a relation between the voltage and the current. It's Ohm's law. The link between them is the impedance. So the impedance times the current gives you the voltage distortion. So if you have some kind of current that you are drawing in a non-sinusoidal way from the transformer voltage will react to that depending on your transformer impedance. And why is that important? It's important because the transformer is supplying the voltage to the full supply that you're having in your factory. So when I have a frequency converter in this room, then the next neighbor room will actually see the distortion that I'm generating on the current, but not on the current directly, but on the voltage. So everything supplied from the same transformer is simply seeing the effect of a non-sinusoidal current drawn. And that means I have a frequency converter. Next door there is a direct online motor, and you can see that direct online motor here on your left-hand side of the picture. If my frequency converter doesn't generate any current distortion, then there is no voltage distortion, and then the grid or the motor in that next door room is running ideal with the ideal conditions. It's of course heating up. It's running the load continuously without issues. And now I start my frequency converter in this room. It's so big that it actually impacts the voltage distortion because the impedance of your network is too low. And then that direct online motor now will start heating up. It sees a distorted voltage, and because the voltage is distorted, the motor is heating up. In the lower hand corner here on your left side screen, you will see that the motor in the lower picture here is significantly running more hot than the motor that doesn't see a voltage distortion is. The difference between those two pictures is actually 8% voltage distortion. So the upper one is running at no voltage distortion, the lower one is running with 8% voltage distortion. So what you see in this case is that the bearing in the drive end is red, indicating that it's hot. What you normally will see here is that the oil in the bearing will vaporize over time, and then you have a bearing failure in your drive end bearing. So the motor will break down. You will not see the lifetime of the motor that you had expected. And you will probably say, well, it's because of unalignment or because it's fed from a transformer that is non-ideal. But the thing is, it's because of voltage distortion. So where you might think that the effect of harmonics is something that you see here now, normally what the effect of harmonics is actually premature aging on your equipment. So the reason why you need to look at this is simply to get the best condition, the best bang for your buck, ensuring long lifetime of your installation. There is, when you go into IEEE 519, you will actually see curves that describes how much you can load your motor depending on your voltage distortion. And there is this curve showing that. And when you are at 8% voltage distortion, the maximum allowed loading percentage on your direct online motor is 85%. So you cannot, if you have a 100 kilowatt motor, you can only load it to 85 kilowatts if you have a 8% voltage distortion. And that of course means you have to oversize, and it becomes a matter of money again. The power utility is also trying to do whatever they can to lower your blocking of the current. If they can give you more, or they can utilize the power supply more efficiently, then of course they don't have to have the same infrastructure. They don't have to do the same investments. And also from the power utility, you will see more and more stringent requirement on the voltage distortion, simply to avoid these phenomena. If things get really high in distortion level, when you are exceeding 10, 12, 15% voltage distortion, then you will start seeing it in your installation immediately. You'll start see lighting flickering, so you'll see things falling out of synchronism. You will see different behavior and erratic behavior on your installation. And that's of course the extreme condition. Before that you will see the aging phenomena. Now, what is a safe level? Should you always be doing something about it? Well, it's all a matter of having equipment that is more immune than what the maximum distortion is. You see the same when we're talking about EMC. You have to have equipment that is more immune than the maximum condition around the equipment is. And it's the same for harmonics. There are standards saying how much the maximum allowed distortion on your power supply is allowed to be, and then we have to build our equipment to be more immune so that there is always some margin between them. There are different regulations in the world. We normally see the IEC standards or EN standard, the international standards for harmonics, defining 3 different levels of harmonics or maximum harmonic distortion on your voltage. There is nothing in there defining maximum distortion on the current. So there are no standards saying that you are not allowed to distort on your current. They are all focusing on the voltage. And the IEC has these 3 values, 5, 8 and 10%. The 5% is commercial buildings. So if you're doing a HVAC installation on a building, then you have to ensure that your installation is not bringing the voltage distortion higher than 5%. When you are having an industrial environment, that could be a big industrial plant, a chemical plant or a textile plant, it doesn't really matter, where you are fed from a general a public transformer, then you are allowed to make 8% voltage distortion. And then last but not least, if you have your own transformer, then you can produce a lot of distortion because you're not polluting anybody else, you're only polluting your own environment. It's only you who will see the effect of aging, and therefore of course you're also allowed to do more distortion. In other parts of the world, you will see IEEE 519 standards, for instance, the normal use standard in US and also in most of Asia Pacific. And they are actually having the same limits. They are also focusing on bringing the voltage distortion down to 5%. And then there are some people who have misused this standard to say that it's 5% on the current distortion. That's actually not the case. It's not a standard for products, but it's a standard for the transformer. And it has the same kind of overall principle as the European standard, namely to bring the voltage level to a low value. In UK you have the 5/4 standard, which is more or less the same thing. Therefore, good engineering practice is to target 5% maximum voltage distortion. Don't consider the current distortion that much because the current we have already done something to. So it's more the voltage that is important here. And the impact on the voltage is of course depending on your system impedance. And then the good practice here, or the guiding star, what are harmonics? Well, it's a byproduct of energy preserving equipment. So UPSs, fluorescent light, frequency converters, power supplies, they are all generating harmonics. So the more of those equipment you're using, the more harmonics you will see on your power supply. Now this 5% voltage distortion is of course a bit difficult because you need to know the system impedance. And the system impedance, that is, you need a lot of information really to judge something about it. So there are some rules of thumb you can use. And the rule of thumb is simply that depending on your transformer loading, if you need to do something or not. First of all, when the amount of frequency converter you have installed is less than 30%, then you don't have to consider harmonic distortion at all. You will always be in a safe level independent of your loading of your frequency converters. If the total amount of frequency converters is not exceeding 30% of the total loading of the transformer, you're home safe, no issues, you don't have to consider anything. If it's higher than 30%, then you need to start doing analysis and see if you're running into areas or not where you will see trouble. The same goes if your transformer is heavily loaded, above 90%, then the transformer is already heating up and it'll be limited how much extra you can load it. And that this little extra percentage that's coming from Harmonics could bring the transformer loading into the red zone. And there again, I recommend you to do some kind of analysis to see if you're home safe, if you need to do something or not. And last but not least, probably the most important part to remember is generator fed supply. That's typically on a marine installation where you have a big generator feeding the entire power supply of your vessel. The generator supply normally has an impedance which is 300 to 400% bigger than the impedance of a transformer. So if a transformer has 5% impedance, then a similar generator delivering the same amount of power would have an impedance of 20%. And that simply means that you will see more effects than the voltage depending on your current, And therefore, if you have a vessel, you need to do something. You need to go in and do the analysis. If you have a hospital supply where you have a backup generator, when the power supply is falling out, you have a backup generator, you need to do the harmonic analysis during emergency operation. What to do, what to calculate. There are a lot of different tools. It's freeware. You can go into our homepage and download it. We have different tools depending on how accurate you want to calculate. And of course, the more accurate you want to calculate, the more data you have to supply. So if you want extremely accurate calculations, then you will also be asked questions about total cable length and how much loading you have of frequency converters and loading conditions and load profiles and stuff like that. And in most cases, it'll be very, very difficult to provide that kind of information. I normally recommend to make a fast calculation just to find the ballpark figure if you have issues or not. And for that purpose, we have a tool also available where you simply tap in the transformer data or the generator data. You put in the frequency converters that you have attached, and then you do a fast calculation on it. And then it gives you feedback how much voltage distortion you can expect from that specific installation. It's easy to use. It gives you a ballpark figure. It's not a 2-digit correct number, but at least it gives you an indication if you need to do something or not. It'll also indicate if you're compliant with standards, so it's easy to know if you're home safe or you have to do something about it. Now, in some cases, you will have to put in mitigation equipment. And I think the first and most important part to remember is if it's not needed, don't add it. It costs you a lot of money. And if you don't need mitigation equipment, it'll just be money down the drain. You'll just throw out money on the street. And that's really a bad investment. So if it's not needed, don't add it. The second thing you have to remember is that if you add mitigation equipment, you need to add the right mitigation equipment. There are a ton of different mitigation equipment that you can use. Passive, active front-end drives, active filters, 12 pulse, 18 pulse, a wide range of different mitigation techniques. And they all have pros and cons. I have seen other drive manufacturing promoting one solution as the wonder of the world that does everything. But there isn't a wonder of the world here. If you, for instance, take in an active front-end drive and you just apply that to all the frequency converter that you're installing, you have to bear in mind that you have just lost 2% of your energy efficiency. And 2% of your energy efficiency, that brings a lot of money in the bank every single year. So you have to go in and evaluate on multiple different parameters. What is important to you? Is it energy efficiency? If that's not the case, you can use AFE. Is it complying with standards? Then some equipment can be used, others maybe not. Are there power factor correction needs? Do you have a special transformer? What is the sizing? How much space do you have available in your installation? So there are many things, many parameters you need to go in and evaluate to find the right and the most used or the best solution for your installation. And if you are in doubt, we are there to help you. Reach out to your local Danfoss guy and ask for advice, and then we'll be happy to help you. With that, I'll close the session and wish you a pleasant day. Thank you.